All right, good morning. Welcome back to Elements of Calculus 2. Today we are going to be talking about how to do limit problems. And specifically today we are going to be dealing with something called L'Hopital's rule. Okay, now you're allowed to use this when you have an indeterminate form. So it's the first thing you're always going to be checking is, do you have an indeterminate form? And you might ask, what the heck is an indeterminate form? An indeterminate form, after you take the limit, just your basic substitution, do you end up with a 0 over 0? Do you end up with an infinity over infinity? Um, do you end up with an infinity minus infinity? That's not 0. Okay, you can't. Infinity minus infinity is not 0. You don't know how big these infinities are. So I know it's very tempting to want to treat these like numbers, but infinity is not really a number. So we can't really just subtract them. Okay? If we end up with like a 0 to infinity, or we end up with an infinity to the 0. Okay, so again, think 0 to something is going to be 0. I'm like, yeah, but it's 0 to the infinity. It doesn't really count as a number like this. And again, infinity to the 0, it's like, it's infinity, anything to the 0 is 1. Like, well, this isn't really anything yet, right? It's not a number. So we can't just plug it in and say it's a 0. It's an infinite is more a concept, not a number. It's a journey, not a destination. Okay. So you have to be really careful about dealing with infinity and be careful not to treat it like it's a number. Okay, so let me go ahead and we'll do an example just to see what's going to happen here. So I would like to figure out the limit. Okay, let's say the natural log of x divided by x minus 1 squared. Okay, and we'll go ahead and do this. So these are the steps you're going to do this. Limit as x goes to 1, rather. X goes to 1. So we go ahead and we say x goes to 1. We say this is the natural log of 1. Okay? And then we have 1 minus 1 squared. The natural log of 1, you remember, is 0. 1 minus 1, of course, is 0. And then look at this. We have a 0 over 0. Hey, that's an indeterminate form. Okay, so that's the first thing we're going to do. You know, I will check this. So if you guys are in my class, or actually if you're in any calculus class, the first thing you want to do is check to make sure, is this an indeterminate form? Because we look for this step, okay, to make sure that you're allowed to use this thing. Okay, it's very powerful, and it will help you solve a lot of problems. You're like, why did I learn all these limits when I was in Calc 1? Because you weren't ready to learn this one yet, okay? But this is very powerful. First step, check to see if it's an indeterminate form. The next thing we're going to do is we're going to go ahead and take the derivative of the top. So we have natural log of x. We're just going to take its derivative divided by x minus 1 squared, and we're just going to take its derivative. This is not the quotient rule. Okay, we're just taking the derivative of the top divided by the derivative of the bottom. This is what a lot of Calculus 1 students wish the quotient rule was, but this is not the quotient rule. Okay, this is L'Hopital's rule. I usually put a little thing in here of saying, like, using L'Hopital's just to let people know what's going on. Okay, so you can see, like, oh, okay, now we're using L'Hopital's rule here. So in order to deal with the derivative of the top, we still have the same limit. We have limit as x goes to 1. Okay, natural log of x is 1 over x, and divided by, now I've got to do a chain rule down on the bottom here, right? So we still have limit as x goes to 1. You could have written this on the outside. I probably should have. But we have 2 times x minus 1, technically raised to the 1, times 1 for the chain. Okay? And now when I plug this in, right, we get 1 over 1 divided by 2, 1 minus 1, which is 1 over 0. This is not an indeterminate form. Cannot use L'Hopital's again. What we're going to do is we're going to take a look at what's going on with the graph here. So remember, like, what 1 over 2x minus 1s look like. And I'm just going back to my basic graph transformations. It's a rational graph. We're going to go over here to positive 1 here. And we're going to go ahead and look at what's happening on this side. And we're going to look at what's going on with this side. So as x gets close to 1, kind of depends on which side. Are we approaching one from the top, or are we approaching one from the bottom? We're approaching it from both because we don't have a little plus or a minus up here. So in this case, it goes to both positive infinity and negative infinity. In that case, my limit does not exist. Okay, so that would be the answer for this one. The limit doesn't exist. Okay, that's a very plausible solution. That happens a lot. Okay, that we end up with a limit, we'll go to two different places, doesn't exist, you're done at that point. Okay. Let's do a couple more problems with this, just to make sure that we can do this. Okay, and Lhopital's is easy enough that I know that back in Elements of Algebra or Elements of Calculus 1, we did a little chart when we started putting more and more numbers in as we got closer and closer and closer. That's a little tedious. We don't really want you to solve limits that way. In Lhopital's, we're going to solve limits this way. And then we're going to need to use those because the next section we're going to be dealing with integrals or limits with integrals in them, integrals with limits in them. So this is going to come in handy for the next section. Okay, so let's see here. We have the limit as x goes to 2. So notice that in my little problem here, with my indeterminate form, we only care about what the answer is going to be. We don't care about what the limit is going to. I mean, most commonly it's going to be to 0, positive infinity. It will occasionally be to an actual number, but for the most part, that doesn't, L'Hopital's doesn't say you can only use it if. Like, no, you can only use it if you have an indeterminate form. It doesn't matter what the limit is going to. So please try to remember, like, I don't care about this part at all. Okay, 5 plus 32, and then we'll say divided by x minus 2. Well, on the bottom, that's not too bad. We get 2 minus 2. That'll be out to be 0. On the bottom, or on the top rather, this is going to be a little bit more interesting to deal with. So I've got, let's go ahead and do this problem. So we've got 2 raised to the 7th power, okay, minus 5 times 2 raised to the 6th power, plus 5 times 2 to the 5th power, okay, plus 32, fingers are crossed. Got this out of my book, so I'm hoping, oh, look at that, it's 0. What a coincidence. So we end up with a 0 over 0. This is an indeterminate form. Again, when you're doing this problem, I'm always looking for, did you check if it's an indeterminate form? If you don't check this, okay, that you've got an indeterminate form, you will lose points for just blasting ahead and using L'Hopital's. Okay, you have to check indeterminate form first. Now we're going to use L'Hopital's. So we have to take the derivative at the top and then the derivative at the bottom. Well, the derivative of the bottom is going to be very nice. Okay, for the derivative of the top, we got 7x to the 6 minus 30x to the 5th, right? Because we had 5 times 6 there. Okay, so we end up with a 30x to the 5th plus 25x to the 4th. The 32, the derivative makes that go away. And we still have a limit as x goes to 2. Okay, so we'll go ahead and we'll plug that in and see what happens. Okay, so we'll go ahead and do this. Again with the calculator, and I'll say this is 7 times 2 raised to the 6th power. Okay, minus 3 times x to the 5th power, so it's minus 3 times 2 raised to the 5th power. Okay, plus 25 times 2 raised to the 4th power. Right, we end up with 752. Beautiful. Okay, just double checking that I got that right. So 752. And one of the reasons why I would pick a problem like this for you to do is because if people just start plugging in this first part, you just say, well, if it's getting close to 2 and I put 2, 2.1, 2.2, 2.01, 2.001, you might get a really big number here and decide that it's going to be infinite. Or you might get a really small number and decide it's going to be 0. When the real answer, it could be like 1 over 252. You would never see that. Okay, if you were just plugging in a calculator, right? You might be deceived into thinking it's 0. So don't let us trick you. Use the fancier way of figuring out a limit. Don't plug in the numbers and do a little table and do the countdown to it. Try to be a little bit more sophisticated, and we're going to use L'Hopital's when we're dealing with this. So great, my limit here is 752. Okay, that's what my limit. Okay, and that's all we're going to do with this. Let's see here. Perfect. Next one. we have, okay, we have an e to the x, so we have limit as x goes to 0. Okay, we have e to the x minus x minus 1 divided by x squared. Okay, let's plug this in. E to the 0 is 1 minus 0 minus 1 for just that, divided by 0 squared. We end up with a 0 over 0. What do you know? It's an indeterminate form. Almost like we planned this with this section. Okay. So we said, great, it's an indeterminate form. We're going to go ahead and use L'Hopital's. Okay. So we're going to take the derivative of the top. E to the x is just going to be e to the x minus 1. The derivative of 1, of course, is 0, divided by 2x. And we're still taking our limit as x goes to 0. Plug this in. We get 0 minus, so we don't get 0. We get 1 minus 1 on the top, right? Because e to the 0 is 1. Okay, so we get 1 minus 1 on the top. Then we get 2 times 0 on the bottom. So we get 0 over 0 again. What do you know? It's another indeterminate form, which means we can and should use L'Hopital's again. So we're going to go ahead and use L'Hopital's one more time. So we can use this as many times as we need to, okay, until we get an answer. If you've got a thing with a polynomial in it, chances are this is going to drop out sooner or later, okay, because we take derivatives and it's just going to go away. So take the derivative, we get e to the x. The derivative of 1 is 0, so we just get e to the x on the top, and we just get a 2 on the bottom. What was our limit? Our limit was limit as x approaches 0. Plug this in, we end up with a 1 over 2, so our answer is 1/2. Okay? I will almost always, so if you're trying to study for tests, you're trying to do these problems, try to pay attention to problems where you have to employ L'Hopital's more than one time. Okay, I guarantee you that not every problem, not every L'Hopital's problem on your test will be a thing where you have to do it twice, but at least one of them will be a problem where you have to apply this thing twice. Notice when we did it, before we did it the first time, we checked, is it an indeterminate form? Yes, use L'Hopital's. Then we took L'Hopital's, we checked, is it an indeterminate form? Yes, it is, use L'Hopital's. You're going to repeat that cycle over and over and over again, okay? If I would go ahead and do music, I would say repeat. Okay, just we're going to do L'Hopital's over and over and over again, checking the indeterminate form, then taking the L'Hopital's until we get an answer. And that answer might be 0, that answer might be undefined, it does not exist, that answer might be something like a half, or 752. Okay, so that's the idea for L'Hopital's, and we could do some more problems later, but that's what I wanted to get out to you guys for today. So practice some L'Hopital's. Thank you very much for watching the video, and I will see you in the next one.